Welcome to Calculus. I'm Professor Greist, and we're about to begin Lecture 14 on Optimization.
One of the best applications of derivatives is to a class of problems you may have called max-min. The modern terminology is optimization. In this lesson, we'll use derivatives to compute maxima and minima for optimization problems, solving some that are simple and some not so simple.
Optimization theory is a wonderful class of problems to which calculus applies. In optimization, you ask, what is the best? How do you maximize profit? How do you minimize drag on an airplane wing? How do you find the best route through a complex network? These are all aspects of optimization. A simple question to which calculus can be applied is, given a function, what is its maximum or minimum value? Well, I'm sure you've seen something along these lines before, but let's step back and think for a moment. If we have a function and we take a close look at its graph, then one of the things that we can observe is that if we are at a place where the derivative is non-zero, then we are certainly not at a maximum or a minimum, because if we zoom in and look at the local behavior at a point where the derivative is not zero, then because derivatives connote rates of change, then if the derivative is negative, that means the function is decreasing locally. On the other hand, if the derivative is a positive value, then the function is increasing locally as we increase the input. Now, of course, we can run that observation in reverse. If we do have a maximum or a minimum, and the derivative exists there, then it must be equal to zero. This motivates the following definition. A critical point of a function f is an input, a, at which the derivative vanishes. So, for example, if we look at a location where there's a minimum, that's a critical point. If we look at a location where there is a maximum, that, too, is a critical point. However, there are critical points that are neither maxima nor minima, such as an inflection point. And in general, the collection of critical points for a function is strictly larger than the collection of extrema, places where you have a max or a min. Now, things are a bit more complex than this, really. What happens if we have a function that is discontinuous, or not differentiable at a point, or not defined at a certain input? Well, a lot of different things can happen. Maxima, minima, neither. We want to expand our definition of a critical point to include as well those locations at which things go bad, such as where the derivative is undefined. The classification of critical points into maxima, minima, or neither is subtle. You may recall the wonderful second derivative test that is so helpful. Recall that at a critical point, x equals a, you have a minimum if the second derivative at a is bigger than zero. You have a maximum if that second derivative at a is less than zero. If your second derivative is zero, or is undefined, then you have a fail. The test does not tell you whether it's a minimum or a maximum or neither. Now, these are only local minima or maxima, since you're just using derivative information. And some students get things mixed up. What do you do? Is it positive for a minimum or positive for a maximum? Negative? Which is it? I'll leave it to you to come up with a way to remember how this goes. Now, why is it that the second derivative test works? Well, as with the case of L'Hopital's rule, there's a good reason, and Taylor series allow us to see that reason transparently. Consider what happens at a critical point x equals a. If we Taylor expand f about that point, then what can we say? Well, because we have a critical point, the first derivative vanishes. Then, with that gone away, and ignoring all of the higher order terms, that is, terms of degree 3 and greater, what do we see? F looks like a quadratic. You have a constant term, and then the leading term after that is quadratic in x minus a. That means, ignoring the higher order terms, that the graph looks locally like a parabola. That parabola would open up if the coefficient in front of the second degree term is positive. That would open down if the coefficient is negative. Therefore, we see that the sign of that second derivative at a tells us whether we have a local maximum or a local minimum.